Okay, so now that we're all experts on bonding theory and we can all draw Lewis structures for any molecule in the universe, right? Hopefully. Now let's look at the actual shapes of molecules, or what we call molecular geometry. I know a lot of you guys didn't even like regular geometry. Now we're making molecular kind, right? Um, Luckily, there's no proofs or any of that garbage in here. It's simply looking at the shapes of molecules. Remember, whenever we drew our Lewis structures, I kept saying that Lewis doesn't care what the actual shape is. So you could draw the bonds at angles or straight across from each other or however you like, and Lewis doesn't care. Because all he's interested in is who's bonded to whom, and how many lone pairs and things like that there are. And so Lewis's model is very effective at doing that. But what it doesn't do for us is show us the actual shapes of the molecules. Now, the theory we have that does that, it's really just a vague theoretical model. It doesn't get into real deep quantum mechanics. We do have better models that I'll talk about briefly at the end of the chapter. But that model, that theory that helps us to explain why molecules get the shapes they do, is called VSEPR, or VSEPR theory. Yeah, I know we kind of pronounced it wrong. That stands for valence shell electron pair repulsion. Now, what does that mean? First of all, valence shell. We know what that is. That's the outer shell electrons. Those core electrons in level 1s2, 2s2, all that nonsense, no one cares about those. They're buried deep inside the atom. They're full shells. They're stable. They're not doing anything. The outermost electrons, the ones in the valence shell, those are the ones that are going to get involved in bonding. Those are the ones that are going to bond to other atoms and or pair up and become lone pairs or whatever. So they're the electrons we care about. So valence shell, because those are the electrons we're playing with. Electron pair. Electrons pair up. We saw that 2 chapters ago, whatever it was, where we had the spin up, spin down thing, right? So the electrons pair. When they bond with each other, each atom contributes one electron, one spin up, the other spin down, and they pair up. If you have a lone pair, both came from the same atom, but again, they're paired up, spin up, spin down. Now, so valence shell, and there's electron pairs. Repulsion. Well, electrons are all negatively charged, and like charges repel. So these electron pairs are going to repel each other. If I have an atom that has 2 electron pairs around it, those electron pairs are going to repel each other, and so they're going to push each other as far apart as possible and get to the exact opposite side of the atom. Okay, that's all VSEPR theory is basically the idea that these electron pairs repel each other and therefore will get as far apart as they can physically get in 3-dimensional space. And I'll show you the next slide of your book. Then I'm going to go into my own PowerPoint because I don't like the way they do this, as usual. Notice, I should say this also. When we say electron pair, okay, we're kind of speaking very loosely here. They probably should have called it valence shell electron group repulsion, because by pair here we mean a lone pair, a single bond, a double bond, or a triple bond, or even an odd electron in those weird radicals that we saw previously. So a double bond, normally you think of as 2 separate pairs, and they are 2 pairs, but for the sake of VSEPR theory, a double bond is a single thing. Okay, so it counts as a pair, even though technically there's more than 2 electrons in there. Again, it's probably better if we had called it electron group repulsion, but they didn't ask me before they did this, so whatever. On the next slide, they kind of show, notice the carbon dioxide molecule. Now, we drew it linear because Lewis doesn't care, but we could have bent it at an angle and Lewis still wouldn't have cared. But now, if we look at the central atom, carbon, notice it's got its octet, 2, 4, 6, 8. That's why we formed those double bonds. But for VSEPR theory, we treat a double bond as just one thing. So carbon has one grouping, quote, pair of electrons around it. I actually did air quotes, you can't see it. The carbon has, here's one grouping or pair of electrons, and then over here, this other double bond is another grouping, or loosely speaking, pair of electrons. So carbon has 2 pairs around it, okay? And VSEPR theory says they're going to repel each other. So if this electron grouping is here on the left of carbon, the other grouping is not going to be over here on the left also. They're pushing each other apart. They're repulsive. Okay? It's like some of you in my class, right? You're repulsive and then people move far away from you. And so the other pair will push all the way over here. Now, can it go further? No, because then it's coming back around and getting closer. So as far apart as it can possibly get is opposite side of the carbon atom, which means there's a bond angle in here of 180 degrees. So if you look at the carbon to oxygen bond and then the carbon to other oxygen bond and look at the angle between those bonds, it's a 180-degree angle, which they show down here. Okay? That molecule, you'll notice, has the atoms all lined up, not bent at some weird angle. So we call this a linear molecule, or linear geometry. The carbon dioxide molecule is a linear molecule. Unlike the water molecule that we saw way back in chapter whatever it was, is bent at some angle, right? The carbon dioxide molecule is not bent at an angle. It's linear because there's only two pairs there, and as far apart as you can get is opposite sides. Okay? That's the kind of thing we're going to be doing in VSEPR theory. Well, in fact, we did it already. But obviously, just having two pairs makes life real easy. They're always on opposite sides. Having 3, 4, or more pairs, things get more complex. Now, you may be wondering, who cares? How do we even know? Well, it turns out, yeah, they can actually do X-ray scattering experiments and find where the nuclei are. So they can literally see the oxygen, carbon, and oxygen nuclei. And they can see they're lined up, not bent at some angle. If you do the same experiment with water, you see that the hydrogens and oxygens are bent at some angle relative to each other. So they can actually really physically measure these bond angles. So if nothing else, we can test this theory and see if it's correct. And it is. But the broader picture does it really matter other than, hey, great, I was right about the bond angle? Turns out, yes. A linear molecule, these bonds are symmetrically arranged around the carbon. And so whatever this is doing, notice, by the way, this is a polar bond, isn't it? Remember your electronegativity differences. Carbon to oxygen, you get an electronegativity difference of around 1 or so. Maybe bigger, I don't remember offhand. But certainly it's a polar bond. Well, this bond over here is also a polar bond. Notice they're exactly opposite sides. The negative on this oxygen, the negative on that oxygen kind of pull exactly apart from each other and cancel out, making the overall molecule behave fairly nonpolar. Even though it has polar bonds, the molecule behaves in a nonpolar way. And for one thing, that means it acts as though it doesn't have much charge distribution to it, and therefore has very poor solubility in water. The molecules don't tend to stick together very well, and so it remains in the gas state rather than becoming a liquid like water is. If this molecule had been bent at an angle, the charges would not have canceled out, and it would have behaved as a polar molecule like water. They'd stick together very well, like water molecules do, and so carbon dioxide would be a liquid or a solid at room temperature. In reality, we know it's a gas. Or another way to look at it is, if water molecules were linear like CO2 is, water molecules would be nonpolar. So they wouldn't stick together, and water at room temperature would be a gas and not a liquid, and we wouldn't exist because we're basically liquid water with proteins dissolved in it. Also, you recall, we needed that bent angle to have that charge distribution so we could dissolve salts and things back when we were doing solubility tables and all that. So if water were linear, it wouldn't dissolve salts. None of those salts we looked at would be soluble very well in water. So all the chemistry we learned about this year involving aqueous solutions works because water is bent at an angle and not linear like this carbon dioxide molecule. You exist because water is bent at an angle and not linear like this carbon dioxide molecule. So this molecular geometry stuff really does matter. At least, to a chemist who actually wonders about this stuff. Now, let me switch gears here and go over to my PowerPoint because I like that better. Here's where I summarize what VSEPR stands for again, so I won't go back into that. But I wanted to show you this, the way we figure out the numbers of pairs and all that stuff. So I might as well do well, there. We use what we call AXE notation, AXE. A is the central atom. In my water molecule here, that means it's oxygen. Okay? X is the attached atoms, chemical X, right? In this case, they're hydrogens. But in general, they don't have to be hydrogen. They can be anything. They can be a chlorine and a bromine. They don't even have to be the same element. So, and then X is how many of those you have, and then E is the empty pairs or lone pairs. So in that terminology, a water molecule, and here's the Lewis structure for it, oxygen, bond to hydrogen, lone pair, lone pair. If you want to take a quick moment to build the Lewis structure yourself and make sure you agree with this. So in this so-called AXE notation, a water molecule has an oxygen, chemical A in the middle, two bonds, they're both hydrogens, but who cares? Those are the X's, and then two lone pairs, or two empty pairs. So it's A, X2, E2. Okay, so it makes it really easy to see that you have two bonds and two lone pairs, A, X2, E2. Okay, now you got four pairs there, that means. Those pairs, two of them are bonds, two of them are lone pairs, but who cares? They're electron pairs. Those four pairs are going to get as far apart as physically possible in space. When you had two pairs, it was easy, they just opposite sides. But how do four pairs get as far apart as possible? Or three pairs for that matter, or others. And that's really the big thing with VSEPR. So we end up with 5 basic shapes, which I'll summarize here briefly, and then tomorrow we'll look at the gory details of specific molecules and how they get these shapes and variations of the theme. But if you have two pairs, as this molecule does, element in the middle, 1, 2 bonds, no lone pairs. So this could be beryllium hydride, for example. Notice here we show it as balloons. Here's the element A nucleus in the middle. Here's an electron pair. There's an electron pair, showing the lobes, the electron clouds maybe a little bit as balloons. Notice if you did that, tied two balloons together at the nucleus, they would naturally go at a 180-degree angle from each other. That's just because they repel each other. So that is a linear molecule. Whenever you have two pairs, it's linear. The bond angle is 180. If you have three pairs, the furthest apart they can get from each other is a flat equilateral triangle. So drawing it down here as a molecule, there's the central atom. There's the three atoms attached, or the three electron pairs really attached to it. Notice an equilateral triangle, each internal angle is 120 degrees. I know the angle up here is 60 degrees, you know, from geometry, but the internal angles here are 120 degrees. So we refer to this shape because we can't just say it's triangle shape. That's way too easy. We have to make it sound more complicated. We call it a trigonal planar shape. It's a trigonal meaning triangle shaped, and it's planar meaning it's flat. Okay? What if you have four pairs, like the water molecule did? Two shared pairs, two unshared pairs. In that case, you're tempted to say it's going to be a square. But think three-dimensionally. You can push a pair up above the square and a pair down below it, and then spread everyone out more. That gives us a tetrahedral shape. Okay? Down here we see a tetrahedron. For you Dungeons & Dragons people, it's a four-sided die. So if you do magic missile damage, you've used that already. So notice the central atom, and then 1, 2, 3, 4 bonds or lone pairs pointing to the corners of the tetrahedron. Tetrahedron is just an equilateral pyramid. Now, if you have 5 pairs, which now you have to have an expanded octet, don't you? Now you get what we call trigonal bipyramidal. So you have a trigonal pyramid, not a tetrahedron because it's not bent down at the bottom, you see, and then another one below it. Now that one we'll talk about more later, but you get some weird bond angles in there. But I'm almost out of time, so the last one, if you have 6 pairs, you have an octahedral shape. it's an 8-sided solid, an 8-sided die for you D&D players again.